Okay, now we're going to start with the new chapter. The section 4.1. It's extrema on an interval. Extrema is basically referred to either maxima or minimum. Okay. So first of all, we will try to understand the definition of extremas of a function on an interval. Understand the definition of relative extrema of a function on an open interval. Find extrema on a closed interval. Okay, extrema of a function. Again, extrema is also referred to maximum or minimum of a function. In calculus, we devote a lot of effort to determine the behavior of function f on the interval I. Does f have a maximum values on the interval I, or does it have a minimum value on the interval I? And where is the function increasing? Where is the function decreasing? In this chapter, we will learn how derivative could be used to answer these questions. So first of all, let's take a look at the definition of the extremas. That will be defined on the interval I containing C. If f of C is the minimum of f on I, meaning f of C is the smallest value, smallest y value on interval I, then f of C is the minimum. So if f of C is the largest value, y value, I, then it's a maximum. F of C is a maximum. The minimum and maximum of a function on an interval are the extrema values, or extrema. The singular form of extrema is extremum of the function on the interval. The minimum and maximum of function on the interval are also called absolute minimum or absolute maximum. You can also say that global minimum or global maximum. They are the same term, right? Absolute minimum, absolute maximum. So let's take a look at two graphs, okay, with the same function, f of x equals to x squared plus 1. The left graph, it's a closed interval from -1, this is -1, to 2. Okay, that's 2. Okay. On this closed interval, as you can see, right, we see a minimum here, so minimum occurs here, maximum occurs here. So for this closed interval, both absolute maximum and a minimum occur. If you look at the graph on the right, now it's on an open interval. This is open interval, meaning we're not including endpoints. So that's why we have a circle here on endpoint. You can see we only have a minimum occurs here, right, at 0, 1. So no maximum, right, only minimum, only absolute minimum occur. Okay, so that's the difference between an open and a closed interval. And let's take a look at this graph really quick. Figure 3.1. If you look at it, this is a piecewise function. G of x equals x squared plus 1 when x is not equal to 0. When g of x equals 2 when x is equal to 0. So that's why we have a circle here. It has a solid point at 0, 2, right? And if you look at it, in this case, our minimum occurs here actually, right? However, this circle here is not a minimum. So maximum we know that occurs here. A minimum does not occur here. Okay, not a minimum. In this case, for the piecewise function, we only have a absolute maximum. Okay. So based on the three examples, we know that if f is continuous on a closed interval, square bracket a comma b square bracket, then f have both a minimum and a maximum on the interval. This is not so the example we just went over, this is not a differentiable function because it's not continuous at x equals 0, right? So it's not continuous function, then it's not differentiable. So if it's continuous, f is continuous on a closed interval, then guarantee that's absolute maximum and absolute minimum on the interval. So this is the extreme value theorem under condition that the function f is continuous. F is continuous. On a closed interval, AB. Okay. So next thing, let's take a look at relative extrema and then critical values. Based on the term, relative extrema is referred to relative minima and relative maxima. So let's take a look at this graph. This is a typical graph which has a hill and a valley. And this is a typical hill, that's a typical valley. Okay, so in this case, f of x equals x cubed plus minus 3x squared, that's a function, has a relative maximum at a 0, 0. So this is what they call relative maximum. And this is what they call relative minimum. And there's no, since the graph go up and down forever, so there's no absolute maximum or minimum. Okay. So informally, you can, for continuous function, you can think of a relative minima as occurring on a hill on a graph. Whenever you have a hill-shaped graph, then you have a relative maximum and relative minimum as occurring in a valley on a graph. So whenever you see a valley, then you have a relative minimum. So such a hill or valley could occur in two ways. If the hill is smooth, or if a hill or valley is smooth and rounded, the graph has horizontal tangent line at a high point or a low point. If the hill or valley is sharpened and peaked, the graph represents a function that is not differentiable at a high point or low points like this, right? So this is not differentiable, not differentiable. This is like the sharp, right? Sharp point, sharp case. or picked, something like. This is not differentiable neither. Okay, so not differentiable case. And here like that, valley like that, right? Here, this is valley. Okay, so for different scenario. So for here on the valley, you have horizontal tangent. If the hill or valley is sharp and picked, then the graph represents a function not differentiable. Okay. So let's take a look at the definition of relative extrema. So if there's an open interval containing C, on which FC is a maximum, FC is called relative maximum of F. You can say that has relative maximum at C comma F of C. And remember, this is the open interval case. Okay. So second one, if there's an open interval, again it's open interval containing C, F of C is a minimum. The F of C is called relative minimum of F. If you can say that F has a relative minimum at parentheses C comma F of C. The plural of relative maxima is relative maxima. Plural of relative minima is relative minima. Relative maximum and relative minimum are sometimes called local maximum or local minimum. And the other one is global, and this one is local. Okay. Find the value of the derivative of each relative extrema shown in figure 3.3. And first one, relative minimum, relative maxima occurs at 3,2. At 0.32. Second graph, f of x equals the absolute value of x. Next relative minima occurs at 0, 0. And the third graph is a sine function, so relative maxima occurs pi over 2, comma 1. And relative minima occurs at 3 pi over 2 and negative 1. Okay. As you can see, this is a horizontal tangent here, right? That's horizontal tangent here. Slope of tangent line equals 0 because tangent line at that point at both hill and then valley is equal to 0. Okay. And here this is not differentiable, meaning not differentiable. Slope of tangent line does not exist. So first of all, in order to solve this, we gotta find the derivative of this f of x. Okay. Now x squared minus 3 over x cubed. In this case, f is equal to 9 times x squared minus 3. So it's 9x squared minus 27. So f prime equals to 18x minus 0, which is just 18x. Okay. And g equals to x cubed. So g prime equals 3x squared. Then we apply the quotient rule. Prime g minus fg prime over g squared. Okay. So f prime, which is 18x, times g, which is x cubed, minus f, which is 9x squared, that's 27, g prime, which is 3x squared, over s cubed squared. Then we just gotta simplify this. We have 18x to the fourth minus 27x to the fourth plus 81x squared over x to the 6th. So now we have a negative 9x to the fourth plus 81x squared over x to the 6th. And you can reduce every single term by x squared, so we end up with 9x squared plus 81 over x to the fourth. Okay, then you set this equals 0 and then solve for set negative 9x squared plus 81 over x to the fourth equals 0, and solve for x. In this case, we have negative 9x squared plus 81 equals 0. So simplify that, x squared minus 9 equals 0. So x equals to plus minus 3. Okay. And so when x equals 3, the y value f of 3 equals to 9 times 3 squared minus 3 over 3 cubed. So that's going to be 9 times 6 over 27, which gives us, reduce it becomes 2. So 3, 2, that's why we have a relative maximum there. Okay. At x equals 0, derivative of f of x equals absolute value of x does not exist because one side limit does not equal to the other side. So left hand side we get a limit which is negative 1. Right hand side limit equals positive 1. So two limit does not equal to each other. So derivative does not exist at that point at x equals 0. Okay, so it's not differentiable. The last one, derivative of f of x is apparent of x equals to derivative of sine x becomes cosine x, and set equals 0. Once you set cosine x equals 0, x is either equal to power 2 or 3 power 2 within the first period, right? And that's why relative maximum occurs power 2, 1. And relative maximum minimum occurs at a 3 power 2 and negative 1. Okay. Once you figure out the critical numbers, and this is what they call critical numbers. Notice that the derivative either in each relative extreme case, the derivative either is a 0 or does not exist. So the x value at this special point are called critical values, critical numbers. Okay. Following are two typical critical numbers. First one is called horizontal tangent. So critical numbers either occurs at when you have a horizontal tangent line. Either a valley or hill. Second one is a derivative f prime of c. Derivative of that point does not exist, meaning slope of tangent line at that point does not exist. Slope of tangent line. Does not exist at x equals c. So two cases when you have a critical numbers. Okay. So definition of a critical number, the f be defined as c. A prime of c equals 0, or if f is not differentiable at x at x equals c, then c is the critical number of function f of x. Relative extrema occur only at critical numbers. So if f of relative minimum or relative maximum at x equals c, then c must be a critical number of f. Okay. So critical values only occur at the critical numbers. Finding extrema on a closed interval. So there are 4 general steps. To find the extrema of a continuous function f on a closed interval, square bracket a comma b, square bracket, use the following step. First step, find the critical numbers of f in open interval ab. The second step, evaluate f at each critical number in ab, in the open interval ab, a comma b. Third step, evaluate f at each endpoint of closed interval, square bracket a comma b, square bracket. And the least of these values is the minimum, the greatest is the maximum. Okay. So basically including all critical numbers and endpoints, and check all the y values correspond to each one of them. Includes all critical numbers and endpoints. And then compare y value correspond to each one of them. Corresponding to each. And then the smallest value is the minimum. And the largest value is the maximum. So let's take a look at this concrete example. Find the extrema of f of x equals 3x to the 4th minus 4x cubed on the closed interval -1, 2. So first of all, find the derivative using the power rule, right? 3 times 4 and reduce the power by 1 minus 4 times 3, reduce the power by 1. So get 12x to the cube minus 12x squared. Now we factor this, we get 12x squared, x minus 1. And we use zero factor property, so setting 12x squared equals 0, setting x minus 1 equals 0. When we solve 12x squared equals 0, x squared equals 0, x equals 0. Second one, adding 1 from both sides, x equals to 1. So there are 2 critical numbers. They both they both belong to closing interval -1, 2. Okay. That means we gotta check 4 things, right? First thing, we gotta check both critical numbers. So when x equals 0, f of 0 equals to 3 times 0 to the 4th minus 4 times 0 to the 3rd, which is 0. 0 minus 0, 0. Second one, x equals 1. So f of 1 equals 3 times 1 to the 4th minus 4 times 1 to the 3rd, which is 3 minus 4, -1. Third one is the endpoint, right? The left endpoint, x equals -1. So f of -1 equals 3 times -1 to the 4th minus 4 times -1 to the 3rd. So here we have a -1 to the 4th becomes 1, -1 to the 3rd becomes -1. Now we have 3, -4 times -1 becomes 4, 7. Okay, the last one we're going to check the right endpoint, x equals 2. The f of 2 equals to 3 times 2 to the 4th minus 4 times 2 to the 3rd. So which is 3 times 16 minus 4 times 8. So it's 48 minus 32, which gives us 16. And now you compare all the y values, right? So since this one 16 is the maximum, then that's your relative maximum. That's your maximum. And this one is absolute maximum. Okay. So the absolute maximum occurs at 216, and relative absolute minimum occurs at -1 is smallest value, so it's 1, -1. Okay, so by doing for this procedure, you'll be able to find out both extremas. Okay. Just repeating what we have, and by using the table summarize what we have done so far, right? Find left endpoint, critical values, second critical values, and right endpoint, and compare all the y values. Eventually you find that the absolute maximum, this is absolute, occurs at 216. And then absolute minimum occurs at 1, -1, just like what we did. And the graph confirms what we discover. As you notice that critical value when x equals 2 does not either yield relative maximum or relative minimum, and that's totally normal. This tells you that the converse of theorem 3.2 is not true. In other words, the critical numbers of a function may not produce either maximum or minimum. May not produce the extremers. Okay.